Hi everyone, Karen Cecilia here. I am trusting that you're listening to the stories and I'm trusting that you're having fun and I'm trusting that you're learning something. And I'm very happy to bring these stories to you. And so I'd like to bring another one to you. Um, Let me tell you what jumping genes are. It's a popular term that is used instead of saying genetic transposition. Um, Genetic transposition is a popular thing they use, jumping genes. And it suggests that genes can move or jump between locations on a chromosome, which regulates gene expressions, and I don't know, and does that all kind of foolishness that they say that it do. I'm just doing after what I do. Why am I telling you that? Because I'm going to tell you the story of the lady who discovered that genes can move. And that's a big thing. Really, really big thing. It might not be. I mean, by the time you're a listener, you go and you check and you read again, you're going to discover that that is a really, 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 really big thing. All right? The other thing I'd like to tell you is that the Nobel Peace Prize for medicine has never been given to one single person alone. Every time they announce a Nobel Prize for medicine, it has always been two or three persons because there are so many discoveries taking place on a daily basis that it is hard for them to honor everybody with it. So it's always two or three persons. But but that changed. This woman changed that. At 81, she won the Nobel Prize. Yep. First woman to win it alone in her field. First woman to win it alone in her field. Maybe I should say is not that they name it. They have more times they name one or two men. They have named a single man before. I do believe that, but they've never named a woman single. It's always two or three of them, which suggests that the women are greater than the men in the Nobel Prize for medicine. And there's a story of Barbara McClintock. Her colleagues called her work ridiculous. For 30 years, they ignored her discovery of jumping genes. And at 81, she won the Nobel Prize, the first woman to win it alone in her field. Barbara was born in 1902 in Hartford, Connecticut, to parents who were unconventional by any era standard. Oh my lord. Suggests that they were weird and funny people, no matter what era they live in. But as a way to describe your parents. Her father, Thomas, was a physician who tried to incorporate holistic approaches into medicine, a philosophy at that time that was professionally disastrous. In the early 1900s, in medical practice, that was not accepted. But his unorthodox views made it difficult to maintain a steady practice. So that forces the family to move frequently. Her mother, Sarah, came from a wealthy, established American family who had opposed her marriage to Thomas because they thought that Thomas was a quack. She was educated, artistic, and a talented pianist and poet. She had defied her family to marry for love rather than social position. Hail to Sarah for that. Both parents were freethinkers. Both Sarah and Thomas were freethinkers who questioned social norms and encouraged their children for independence. Their daughter Barbara inherited that fierce independence, and perhaps, looking back on things, maybe too much of it, even for her unconventional parents. From her earliest years, Barbara preferred solitude. She would play alone for hours, content with her own company. She was brilliant, intense, and completely uninterested in conforming to expectations for girls. Her mother actually worried about her. Barbara seemed too independent, too solitary, too unconcerned with being likable or fitting in. She just didn't care. But Barbara wasn't lonely. She was focused. At Erasmus High School in Brooklyn, New York, Barbara discovered science. She was captivated by the idea that nature followed invisible rules, patterns that could be discovered and understood through careful observation. In 1919, at age 17, Barbara entered Cornell University. She intended to study plant breeding, but quickly discovered genetics, which was at the time a relatively new field that was just beginning to understand how traits were inherited. Barbara was enthralled. Genetics combined everything that she loved: careful observation, pattern recognition, intellectual puzzles, and the chance to discover something entirely new. She was also one of the very few women in the program. Cornell's Agricultural College admitted women, but they were a small minority, often dismissed or ignored by male professors and male students alike. But Barbara, being her solitary self, didn't care. She dove into research with an intensity that surprised even her professors. She worked on corn genetics, studying the chromosomes of maize plants. She developed techniques for visualizing chromosomes that were more advanced than anything being used at the time. She earned her PhD in 1927 and continued researching at Cornell, making significant discoveries about chromosome structure and behavior. But as a woman in 1930s academia, Barbara couldn't get a permanent faculty position. Not even because her mother was rich and come from a good family. Not even that could help her. She was a woman, white as she might have been. Universities just didn't hire women for tenure tracks jobs. She survived on temporary research positions. She survived on grants, moving between institutions, never secure, always brilliant, but never fully recognized. Then, in the 1940s and 1950s, working at Cold Spring Harbor Laboratory in New York, Barbara made a discovery that would eventually revolutionize biology. She was studying corn, specifically patterns of color in corn kernels. Let me read it again for you because it's written here. So let me just read that again so you can understand. Barbara made a discovery that would eventually revolutionize biology. She was studying corn, specifically patterns of color in corn kernels. She noticed something strange. Sometimes the color patterns didn't follow the expected rules of inheritance. Through painstaking observation and meticulous record keeping, Barbara discovered something astonishing. Genes could move. In other words, since we're talking about corn, Barbara could take white-looking corn and the yellow-looking corn, and she could combine them or move them from various chromosomes or whatever that they call them, and make it into something else or still corn. That's what I'm understanding from reading it. So I'm just telling you what my understanding is. I could be wrong. For decades, scientists had assumed that genes were fixed in place on chromosomes like beads on a string. But Barbara's corn showed that some genetic elements could jump from one location to another. It is called transposable elements, or what the press would later call jumping genes. But more than that, Barbara discovered that these mobile genetic elements could turn other genes on or off, regulating gene expression in ways no one had ever imagined. In 1951, Barbara presented her findings at a major genetics symposium. The response from the mostly all-male audience was silence, confusion, and then dismissal, because white, male, academia never take anything any woman did or said serious. Her colleagues didn't understand her work. It contradicted everything that they thought they knew about genetics. Some thought she was simply wrong. Others thought her results were artifacts, mistakes in her methodology. Barbara tried to explain, but the scientific community wasn't yet ready to listen. For the next 20 years, Barbara's revolutionary discovery was essentially ignored. She continued her research, publishing papers that were rarely cited, working in relative obscurity. But she didn't stop working because she knew she was right, because the corn didn't lie. But the isolation for her was difficult. Barbara became even more reclusive, focusing entirely on her research, avoiding the scientific conferences where her work was dismissed. Then, in the 1960s and 70s, molecular biology advanced. Scientists developed tools to study DNA directly, and they began finding transposable elements everywhere, in bacteria, in fruit flies, in humans. Barbara McClintock had been right all along. The genes she had discovered in corn in the 1940s weren't an anomaly. They were fundamental in how genetics worked across all life forms. Transposable elements, jumping genes, turned out to be crucial for evolution, for genetic diversity, for gene regulation. They helped explain how organisms adapt, how cells repair DNA damage, how genetic diseases develop. See? Barbara's ignored discovery became one of the foundational concepts of modern genetics. In the late 1970s and early 1980s, the scientific community finally acknowledged what Barbara had discovered 30 years earlier. And boy, the awards and the honors began pouring in. Recognition that came decades too late, but was profound nonetheless. In 1983, Barbara McClintock was awarded the Nobel Prize in Physiology or Medicine. She was 81 years old. She had been working in genetics for over 60 years. She had made her revolutionary discovery 40 years earlier. And she was the first woman to win an unshared, that's the word I was looking for in the beginning, unshared Nobel Prize in medicine. Every previous woman winner in that category had shared the prize with men. That's what I was looking for also. Now we got it. But Barbara won it alone. When she was told that she had won, Barbara's response was characteristically modest. And she remarked, and I quote, "It seemed unfair to reward a person for having so much pleasure over the years, asking the maize plant to solve specific problems, and then watching its responses." End of quote. Modest at that. She continued working until her death in 1992 at age 90. Even in her 80s, she was still growing corn, still observing, still discovering. Barbara McClintock's story is a reminder of how science actually works, not as a smooth progression of ideas accepted by open-minded peers, but as a messy, political, often unfair process where brilliant work can be ignored for decades because it challenges the assumptions or because the person doing it doesn't fit the expectations. It still exists today. That behavior still does. But Barbara was ignored partly because her ideas were ahead of their time, but also because she was a woman, because she was unconventional, because she didn't network or self promote, because she worked on corn rather than fashionable model organisms. She endured decades of professional isolation, of having her work dismissed, of being unable to get the permanent positions and resources her male colleagues took for granted. And she kept working anyway because she knew she was right, because she loved the work, because the corn kept showing her patterns no one else could see. Her independent spirit, the trait that her mother had worried about when Barbara was a child, turned out to be exactly what she needed. She didn't need approval or acceptance or validation to continue her research. She needed only her own corn plants and her extraordinary ability to see what others missed. They called her work ridiculous. They did. 30 years later, it won the Nobel Prize. She was right all along. She just had to wait for the world to catch up. Thank you all for listening. Remember to like and share. God bless you all. Stay safe, everybody, and keep your kids safe.